In the previous chapter, we have learned that a continuous function, let's say f, continuous on a closed interval, say a and b. This function always has a maximum value and a minimum value. So if we draw the graph of this function, let's see, if a is here and b is here, then as long as this is continuous function, then we always have a maximum value and a minimum value. In this case, the maximum value would be this value, and the minimum value would be this value. Okay, and if the function looks like this, for example, between a and b, then the minimum value would be this value, and the maximum value would be this value. So this is the case for continuous functions. And when we take into differentiability, we are not limited to the functions defined on a closed interval. And also, we may not be interested in those maximum values or minimum values per se for the entire interval, right? So this is the maximum and minimum value for the entire interval. So these are called global maximum or global minimum. Okay, it's global maximum or minimum. It's global in the sense that it is defined for the entire interval, closed interval. But sometimes we are interested in local properties, which means if we have a function defined on some interval, maybe it's open interval. So if there is, so let's say within this interval, the real maximum value, the global maximum value may be here. But if we look only around this region, this value is the maximum value within some small area here, region here. So such a point is called a local maximum as opposed to global maximum. This may not be the greatest value or within this entire domain of definition, but it is the maximum value within a small region around this point. So this is global maximum. And similarly, we can define a local minimum. So if you look at point around this region, so this is the minimum point within this small region. It may not be the global minimum, which may be here, but in a similar manner, we can define local minimum. So let's define the notion of local maximum and local minimum more precise. Here's the more precise definition. Let's see. That's local maximum and minimum. So let's say f of x is a function defined on an interval I. And let a be a point within this interval. This interval can be open or closed or semi-open. And we say, so first, we say f of a is a local maximum value local maximum value of the function f of x. So if we say this means this. So there exists some positive real number delta such that for all x within this open interval a minus delta, a plus delta, and x not equal to a implies that f of x is less than f of a. Okay, so if this condition holds, then we say f of a is a local maximum value of the function f of x. And similarly, we say f of a is a local minimum value of f of x. So when we say this means this. If there exists a positive real number delta such that for all x within this open interval from a minus delta to a plus delta, x not equal to a implies f of x is greater than f of a. Okay, so this is the condition for the defining condition for a local minimum value. And if this holds, we also say this. Okay, in the case of a local maximum, we say this a here, and a is a local minimum point. Point, it's not value. And also in this case, we say in the second case, we say a is a local minimum point. So what does this definition mean? Okay, let's look at the first one, local maximum value. So if we take usually small enough delta, then around this region, around this region, around A, around this point A, plus minus delta, this f of a is the maximum value. It's greater than any value within this small interval. So if we plot, so we don't care about any other region, but so if we take small enough delta, so this is A, so this is the interval, this point is A plus delta and this point is A minus delta. So this width is delta. Okay. If we take small enough delta, then within this interval, the value of f of a is the maximum. Okay, within this region. Okay, but if the delta is too big, then, for example, if we take delta really big, like this, okay, this delta, then some other point, for example, in this point may be greater than this point. So in this case, this f of a is not the maximum value within in this range. But what we are saying here is there exists some delta. Okay, so it doesn't have to be any delta. If it's small enough, then that's sufficient for a local maximum. And the same applies for the local minimum. Oh, wait a minute. Let me correct a little bit. So this interval should be not just this, but it's intersection between this interval I and this open interval. Okay, otherwise, sometimes uh, this may go out of this interval, so we should take the intersection. And same for the local minimum. And we also use the term extreme values. Extreme value to mean either a local maximum or local minimum. This notion includes both maximum and minimum. And of course, a global minimum can be a local minimum, but not vice versa. Okay, local minimum may not be a global minimum, but a global minimum is always a local minimum. One simple, probably trivial example is this. F of x is a constant, c is a constant, and defined on all real numbers, for example. So in this case, the global maximum value is c, and the global minimum value is c. It's greater than or equal to any other value, but this is neither a local minimum nor the local maximum. Let's see another example. Consider this function. F of x is defined as x squared minus 1 times x squared minus 4, which is, if you expand, you will have x to the power of 4 minus 5x squared plus 4. And if you factor x squared here, you have x squared minus 5 plus 4. So if you draw the graph of this function, it should look like this. Let's see. So this is x-axis. Let's say this is 1, this is 2, it's negative 1, negative 2. I think it should look like something like this. Well, it's not so pretty, but so it will cross the x-axis at plus minus 1 and plus minus 2. That's for sure, because from here, right? So x squared minus 1 is x plus 1 times x minus 1, and so on. And when x is equal to 0, it has the value of 4, so this value should be 4. And when x is plus minus square root of 5, it is also 4. So this should be square root of 5. That's negative square root of 5. So yeah, if you look at this graph, you see that here's a local maximum. All right, so let's prove this is indeed a local maximum as defined by given by that definition we have just given. So let's see. If we take so we know that this is square root of 5 and it takes the value of 4. So it looks like from this graph that if we take the interval smaller than this, okay, let's see, smaller than this, narrower than this, plus minus square root of 5, then the maximum value within that interval, in this interval, is this point, 4. So let's see, if we take delta equals to square root of 5, which is of course positive, then for all x within this open interval, from negative square root of 5 to positive square root of 5. Then we have, so as long as x is in this interval, we have 0 less than x squared is less than delta squared. Okay, for all x we have this. For all x within this interval we have this. Okay, and if we subtract 5 from each side, each term, we have negative 5, x squared minus 5, and delta squared minus 5. But this one is 0. Okay, because delta is defined to be square root of 5. So if you look at this expression, then we you should know that x squared times x, so x squared is positive, right? So this is less than 0. And if you add 4, this is less than 4. Okay, but 4 is the value of f at 0. So for any x within this interval between negative square root of 5 and positive square root of 5, the value of the function is always less than 4, which is the value at exactly 0. Okay, I mean, as long as x is not equal to 0, of course. Therefore, according to the definition, this value, f of 0, is a local maximum. And x equal to 0 is the corresponding local maximum point. Next, we want to relate extreme values, that is local maximum or minimum, with differentiability of a function. But before that, we need some more extra notions of additional notion like stationary or critical points. Let f of x be a differentiable function. And we say the point A is a stationary point, or critical point. Either one is okay. Critical point. So that means the differential coefficient at A is equal to 0. Okay, and in this case we say f of A is a critical value or critical or stationary value. Is a critical value. Oh, stationary value. Oh, I should swap the order, but either one is okay. Value. Then here is a theorem that connects differentiability and criticality and local maximum or minimum. So if okay, let's say, so let f of x be a differentiable function. on some interval. Okay, and if f of a is a local extremum, that means local maximum or local minimum, then this implies this point A is a stationary point. Okay. Okay, let's prove this. Wait a minute. This is not definition. This is a theorem. Okay, anyway, let's prove this. Uh, this is for extremum, so it can be maximum or minimum, but we prove only for maximum, okay? The case for the minimum, local minimum is the same, but just a little bit of rearrangement. So suppose f of a is a local maximum. That means this a is a local maximum point. Okay, so by the definition of a local maximum, there exists a positive real number delta such that for all x in this interval, a minus delta, a plus delta. In this case, we are not assuming any interval as the domain of definition. So just ignore that, and then for all x, x not equal to a implies and f x less than f of a. But here we loosen this definition so that we may include the case where x is exactly equal to a. So if we include that case, then this is for all x we have f of x less than or equal to f of a. Okay. So so this is the given condition, and since f is differentiable, that means differentiable at, of course, at x, then the derivative at a is limit x approaches a, f of x minus f of a over x minus a. So this limit exists, and if we calculate the right limit first, okay, consider the right limit. That is limit x approaches a from the right. Okay, consider this. So that means x. So we are moving x towards a, so we can assume that x is close enough so that this x is within this interval, a plus delta. Okay, so if we have a here and if we have delta here, a plus delta here, suppose x is somewhere between here, okay, and moving towards a, then in that case x minus a is positive, and since f of a is a local maximum by assumption, f of x minus f of a is less than or equal to 0, because f of a is a local maximum. And x minus a is positive, right? So this means this limit, this right limit, is negative or 0. Okay, and next consider the left limit. So x approaches to a from the left. So in this case, a is here and this is a minus delta. So x is somewhere between these two numbers and approaching to a from the left. So in this case, again, f of x minus f of a is still negative or 0, because f of a is a local maximum. But in this case, x minus a is also negative. So that means this limit, left limit, is positive or 0. Okay? But by assumption, the limit exists. So the right limit and the left limit must be equal. So the only way these two limits to be equal is that they are both 0, right? So that means limit x going to a of this is 0. So that means the derivative of f at a is 0. Okay? Therefore, a is a stationary point. Okay, so this was the proof, but you should notice that the converse of this theorem is not true. It's not always true. For example, that means even if a is a stationary point, it does not mean that f of a is a local maximum or minimum. Okay, one simple example is this function. F of x is equal to x cubed. Okay, and consider x equal to 0. Okay, if you calculate its derivative, okay, so f prime of x is 3x squared, and at x equal to 0, this derivative is 0, but it's not a, so it is a stationary point, but it is not it's not a local maximum or local minimum. So if you plot this function, it looks like this. It looks like this and like this. So this point, at this point, x equal to 0, the gradient of the tangent line is, it's horizontal. It's 0. So derivative is 0. But it's not a local maximum or minimum. In fact, if you magnify the region around 0, it is increasing. It's strictly increasing. Strictly increasing and no maximum or no minimum. The next theorem is called Rolle's theorem. Which states this. Let f of x be a continuous function on this closed interval between a and b. And also assume that this is differentiable. On this open interval. Okay. And also assume that f of a is equal to f of b. So the values are the same at the endpoints. Then there exists a real number between a and b greater than a less than b such that f prime of c is equal to 0. Okay, so if you visualize this situation, let's say this is a and this is b. So the values of this function at the endpoints are the same. So it may be like something like this. So in this case, in this particular case, there are 2 points where the derivative is 0. See, this point and this point. So there may be 1 point, 3 points, many points, but at least there is 1 point such that the derivative is 0. Okay, let's prove this theorem, which is not too difficult. So first case, okay, this case 1, if f of a and f of b, they have the same value here by the given condition, the global maximum and minimum and global minimum at the same time. So if this is the case, then this function must be a constant. Then f of x is a constant. Let's say, well, is a constant. Let's just say constant. Okay, since it's a, this value is both global maximum and global minimum. If it's not constant, then there is a contradiction because let's see. Okay, so let's say this is a, this is b, and they have the same value. If it's not global, it's not constant, then there should be something like this, deviating from this straight line, right? So if that's the case, there is a value that is lower than f of a or f of b, or greater than f of a or f of b. But if that's the case, then it is against, it's in contradiction with this assumption that they are global maximum and minimum. So if this is the case, this function must be constant, and if it's constant, then its derivative is 0. So actually all the values within this interval has this property. Okay, so that's case 1 and case 2. Otherwise, there are local extremum. By the logic we have just explained, there are local maximum maybe it can be multiple maximum, so the plural is maxima, and minima. So at which point, and at these points, from the previous theorem, we have this derivative of f is 0. So that's done. Next, by applying Rolle's theorem, we can prove the following more important general case, which is called the mean value theorem. Okay, again, let f of x be a continuous function on this closed interval between a and b, and at the same time differentiable on this open interval between a and b. Okay, and then there exists some point in this interval between a and b such that f prime of c, so the derivative of f at c is equal to this value, b minus a. So this means, so if we have a function, let's say something like this, and at a it has this value, at b it has this value. So this right hand side means the slope of this line connecting these 2 points. Okay, so this difference is f of b minus f of a, and this difference is b minus a. So this right hand side means the slope of this red line. And so this means there is some point within this interval such that the tangent line, the slope of the tangent is equal to the slope of this line. So for example, in this figure, it could be somewhere here. So this could be C. So if you draw a tangent line from this point, at this point, it has the same slope as this red line. Or also, maybe this point, somewhere here. There could be one or more such points. Okay, so same slope. Let's prove this, and the proof is quite simple. So we just apply Rolle's theorem on an appropriate function. So let's define a function g of x that is f of x minus f of b minus f of a over b minus a times x minus a. Okay, so this is the original function f of x, and this is a linear function. The second term is a linear function. This term is a linear function with the slope of this. Okay, so what's special about this function is that it has the same value at a and b. So g of b is f of b minus f of b a b minus a. So this x is b here, so this will cancel, and this f of b will cancel, and we have f of a here, and g of a is f of a, and if x is equal to a, then this is 0, so it's just f of a. So this value and this value, they have the same value. And of course, by the way this g of x is defined, it is continuous and also differentiable, because f of x is differentiable and this linear function is differentiable. Therefore, we can apply Rolle's theorem, which states that there exists some c between a and b such that g prime c is equal to 0. Okay, so this means if we differentiate g, we have f of x, so replace x with c, then f of b minus f of a over b minus a, and c minus a equals to 0. But wait a minute, not equal to 0, but since we differentiate it, so this should be just this term. Okay, so if we differentiate this one, it will be just 1. So we are just left with this, which is equal to 0. Therefore, f prime c is equal to this value. And we are done. Now, from this mean value theorem, we can derive a few interesting, probably trivial results. First corollary is this. Let's say, suppose f of x is a differentiable function on this open interval between a and b, and identically its derivative is 0. So that means for all x in this interval, the derivative is 0. Okay, so for all x in this interval. Okay, then f of x is a constant function, c, which is a constant. Constant on this interval. Okay, let's prove this. So pick any c from this interval and let capital C be the value of this function at this arbitrary point. Okay, then if x is equal to c, then of course f of x is equal to c, this capital C, by definition. Okay, then consider the case where x is less than c. Then we consider the interval between x and c. Okay, and we are assuming that this function f of x is differentiable in this interval, so it should be also continuous in this interval between x and c. Okay, and of course it's differentiable. So by the mean value theorem, let's see, by the mean value theorem, there exists some d between x and c such that f of x minus f of c is equal to f prime of d times x minus c. Well, in the original form of the mean value theorem, it was this divided by this, but we can just rearrange the expression. So we have this. Okay, but by the assumption that this derivative is always 0, we have this is the right hand side is 0. Therefore, for any x, as long as it is less than c, it is equal to f of c, which is equal to that constant capital C. And the same is true and similar for the case where x is greater than c. We can use again the similar approach using the mean value theorem, and we can show that for any x, it is actually equal to f of c. And we're done. And the next corollary. Again, we assume that f of x is continuous. It's cumbersome to write, so just continuous on this closed interval and differentiable on this open interval. Okay. Then first, if let's say for all x in this open interval, if f prime of x is greater than 0, then this implies f of x is strictly monotone increasing. Monotone increasing on this interval. And similar to this, if for all x in this interval between a and b, f prime of x is less than 0, then f of x is strictly monotone decreasing. On the closed interval. So let's prove this. I only prove part 1, and part 2 is very similar. So what we need to prove is this. For all CD picked from this interval, we just need to show that if C is less than D, then f of C is less than f of D. So this is what we need to show. Okay, so suppose C and D are picked from this interval, and assume C is less than D. Okay, and this function f is of course continuous on this interval and differentiable, so continuous on this closed interval and differentiable on this open interval between C and D. Okay, so we can apply the mean value theorem. So therefore there exists some t between C and D such that f of D minus f of C is equal to f prime of t times D minus C. Okay, but since we are assuming that C is less than D, this part is positive. Okay, and by assumption here, f prime is positive. Okay, so positive times positive, which is positive. Therefore, f of D is greater than f of C. So we have shown this. Just swap left and right, and we have this. So from this assumption, we derive this conclusion. Therefore, this function f is strictly monotone increasing. the next corollary gives a sufficient condition for a local maximum or minimum. Again, in this case, assume this is twice differentiable. Not just once, but twice at least. And also assume that f or f prime of c is equal to 0. Of course, this c is within the domain of this function, and some c between a and b. Okay, then first, if f double prime of c is greater than 0, then x equal to c is a local minimum point. So that means f of c takes a local minimum value. And 2, that's actually opposite of this. F double prime of c is less than 0. If it's negative, then this point c is a local maximum. Alright, we prove only part 1, and part 2 is very similar. So let's start. First of all, by assumption, let's see, by assumption, so we calculate the second derivative according to the definition. So that is the limit x approaches c and f prime of x minus f prime of c over x minus c. But f prime of c is 0 by assumption, so this is just f prime of x over x minus c, and x approaches c. And this is equal to the second derivative at c. And this is assumed to be positive, okay, by this assumption. Now, at this point, we apply the definition of limits. Okay, so the limit of this is equal to this. So first of all, we define epsilon to be this value. Okay, it could be any positive value, right? So let's define epsilon to be f double prime of c. Then, by the definition of limits, we have this. There exists some positive real number delta such that for all x in this interval between a and b, let's see, 0 greater than x minus c modulus less than delta implies this f prime of x over x minus c minus f double prime c less than epsilon. Okay, so this is the definition of limit in the epsilon delta argument. Okay, and from this, the last claim, we can say that this quantity inside here is between negative epsilon and positive epsilon. Okay, but actually we don't need this part. So just from the first inequality, we have f prime of x, x minus c is, let's see, greater than f double prime of c minus epsilon. However, the definition of epsilon was this. So this is epsilon. That means this is equal to 0. So this quantity f prime of x over x minus c is positive. Now consider the following two cases. If x is between greater than x is greater than c and less than c plus delta, then c minus then x minus c is negative. So this implies, since this ratio is positive, this implies that f prime of x is also negative. Okay, so this implies f of x is strictly monotone decreasing function. Strictly monotone decreasing in this interval c plus delta. Okay, so that means if you plot, it should look like, let's see, so between c and c plus delta, it's decreasing, strictly monotone decreasing, something like this. So that means, so this is f of c and this is f of x. So that means f of x is less than f of c. Okay. And on the other hand, if x is between c minus delta and c, then this means x minus c is positive. And this means from this equation, from this inequality, this means f prime of x is positive also. And so this means f of x is strictly monotone increasing on this interval. Therefore, so it will be like c and c minus delta, it's strictly increasing, monotone increasing. So this is f of c and this is f of x. So this means f of x is less than f of c. So either way, f of c is greater than f of x, as long as x is not equal to c. Therefore, f of c is a local maximum. Now this was the definition. Now we have this delta, and within this this interval between c minus delta, c minus delta and c plus delta, within this interval, then f of c is the maximum value. So that was the definition of a local maximum. So that was to be proved. And similar for local minimum. So let's prove only part 1. Okay, part 2 is very similar, so I will leave it as an exercise. First of all, let's apply the definition of differentiation to calculate f double prime at c. So that is this limit. Prove and limit x approaches c, f prime of x minus f prime of c over x minus c. But by assumption, this is 0. So this is just f prime of x over x minus c. And that is equal to f double prime c, which is positive by assumption, this assumption. Okay. Next, we apply the definition of limits here to this situation. Okay, so for that, we define epsilon as this value, f double prime of c, which is positive. Okay. So since this limit is assumed to exist, there should be a positive real number delta such that for all x in the domain of this function, this x minus c less than delta implies the difference between this f prime of x over x minus c minus f double prime of c is less than epsilon. Okay, so this is the definition of limit, right? So the limit of this is equal to this, means this by definition. Okay, now from this part, we conclude that this inside this modulus is between negative epsilon and positive epsilon. But actually we don't need this part, so we use the first inequality here. So from this we have, let's see, f prime of x over x minus c is greater than f double prime of c minus epsilon. But the definition of epsilon was this here. Therefore, this value is epsilon, so we have 0. So this means the quantity on the left-hand side is positive, okay, greater than 0. Next, consider the following two scenarios. First, x is between c and c plus delta. Okay. So this means, let's see, x minus c is positive, right? X minus, because x is greater than c. And because of this, if x minus c is positive and this ratio is positive, it must be that this must imply that f prime of x is positive. Okay, and this indicates that f of x is strictly monotone increasing function on this intervals between c and c plus delta. Okay, and that means, so if you plot, it's easier to understand, I guess. Let's see. So if this is c and c plus delta, it's strictly monotone increasing. So it's something like this. So the value of f of c is less than the value of f of x. So f of c is less than f of x, because of this monotone increasing nature. Okay, and the second scenario, consider when x is between c minus delta and c. Okay, this indicates, this implies x minus c is negative. right? Because c is greater than x. And this implies from this inequality, f prime of x is also negative because the ratio must be positive. Okay, and this in turn implies that f of x is strictly monotone decreasing on this interval, c minus delta and c. And this indicates, let's plot it, so c and c minus delta, it's decreasing, right? So it's like this, or maybe like this, who knows. But in any case, f of c is less than f of x because it's decreasing. So by this and this, on for all x within c minus delta and c plus delta, we have f of x is greater than f of c. Okay, and of course, f of x is continuous in this interval, so this means f of c is a local minimum. Now, this was the definition. Now, there is some delta such that within this interval, this inequality holds. Therefore, f of c is a local minimum. And the proof is done. Next, we would like to define some qualitative description about functions. That is concave and convex. Okay, so let's define it. Definition. Which one is first? Convex and concave. Okay, and let's say f of x is a function defined on an open interval I. And we say f of x is convex. Convex at point C. If this happens, okay, if we draw a graph of f, and this is point C, let's say, and if you draw the tangent line at C, it will be like this. Okay, so tangent at x equal to C. So if all the points of f of x are above this tangent line, then we say f of x is convex at x equal to C. Okay, so but this definition depends on this graphical image. So what happens if the graph is something like this? Does it still apply? We don't know. So more precisely, we use the equations. Okay, so that means, well, of course, it's in the neighbor of C. So let's say if there is some positive real number delta such that, let's see, for all x in the domain of definition of this function, if x is in the neighbor of C, that is x minus c is less than delta and greater than 0. I mean, if in terms of modulus, then this implies let's see, this implies f of x is greater than f prime of c and x minus c plus f of c. Okay, so if this condition is met, then we say f of x is convex at x equal to c. But what does this equation mean? This one. Especially this one. This one is actually the equation of the tangent line, right? So its slope is f prime of c. So it's the slope of the tangent line at point C. And this line, so maybe we should write y equals to f prime of c, f x minus c plus f c. So this is the equation of a line that passes through the point C and f of c, right? C and f of c. So this is exactly the equation of the tangent line at tangent at C. So all the points of x that satisfies this, so that is within some interval delta and delta. Within this interval, all the points of the function f of x is greater, is above the tangent line. So that's what this means. So in this case, it's convex. And similarly, we define concave if the tangent line is above the function, or the function is below the tangent line. So that's intuitively, that's this case. So we have a function like this, and let's say this is C, and the tangent line is this. So all the points of f of x is below the tangent. Then we say it's concave. Concave. Okay, and I hope you know how to define in terms of in this style, using delta and the equation for the tangent line. Now the next is a little corollary based on the notions of convexity and concavity. So it's a corollary. So again, let's assume that f is twice differentiable. Differentiable on an open interval I, and assume this constant c is in this interval. Then first, if f double prime of c is positive, then f of x is convex at c. And if f double prime of c is negative, then f of x is concave at x equal to c. Again, we prove only part 1, okay, and part 2 you should prove as an exercise. Okay, so first we define a new function. Okay, define g of x as f of x minus, let's see, f prime of c, x minus c plus f of c. And you should note that this part is the same as the equation for the tangent line, right? So we know from this definition we can see that g of c, if you put c here, it's 0. And also this g is differentiable, of course, and if you differentiate it and put x equal to c, then we should have f prime of c, and this is a constant, so it will be gone, and this will be 1, f of c, so this is 0. And g of x is also twice differentiable because f of x is twice differentiable, and this is a linear function. It's of course twice differentiable. So let's differentiate it. If you differentiate g of x twice, then that is actually equal to the second derivative of f. You should check that. And by assumption, this is positive. Okay. And from the previous corollary, we see that x equal to c is a local minimum point of g of x. Okay, so that means and also at this x equal to c, g of c takes the value of 0, so that means g of x is greater than or equal to 0. Actually it's greater than 0 if x is not equal to c. So that proves this. So this is always greater than 0. So that means f of x is greater than this. F prime of c, x minus c plus f of c. So by the definition of concavity, this function of f of x is concave. Sorry, it's convex. It's positive, so it's convex. And the proof is done. Let's see one example. That is this function. This function. So exponential of negative x squared. So if you plot this, it looks like this. So it's symmetric, so it's an even function. It has the global maximum value at x equal to 0. And around 0, around this point, it is concave. Okay, but after some point, let's see. But after some point, it becomes convex. So there is some point where convexity changes to concavity somewhere here. So in this region it's concave, and in this region it's convex. And this point where this convexity changes is called inflection point. Inflection point. Maybe the spelling is not right. Inflection. Okay, so that can be found out by just differentiating. So once you differentiate it, you should have, let's see, applying the chain rule, you have negative 2x exponential of negative x squared. And if you differentiate it twice, I skip all the details and just give you the answer. The final result, that should be this. So let us solve f double prime of x equal to 0. So this second derivative becomes 0 if this factor becomes 0. So that means x is plus minus 1 over square root of 2. So at this point, the second derivative is 0. So f double prime of x is negative. And if you check, if x is between these values and it's positive if x is either greater than the positive value or less than the negative value. So this point, x plus minus 1 over square root of 2, so that is this and negative 1 over square root of 2. These points are the inflection points of this function. And finally, for this chapter, I will explain Newton's method, or also known as Newton-Raphson method. This is a numeric algorithm used for solving nonlinear equations. So here it is. Let's say we have a function f of x that is twice differentiable. On an open interval I. And also assume that this open interval I includes a closed interval from A to B. So this closed interval is a subset of I. And we impose the following conditions. First, f of A is negative and f of B is positive. And second, for all x in this closed interval, the derivative is always positive, and the second derivative is also positive. Okay, now then we define a sequence Cn by this. So C1 is B, and Cn plus 1 is Cn minus f of Cn over f prime of Cn for n greater than or equal to 1. Okay. Then we have this this sequence actually converges. Then this sequence converges to alpha, where alpha is the unique solution of f alpha is equal to 0. So this means the following scenario. So let's see, we have a function f of x, and let's say this is b, and let's say this is a. Let's say this is a. Okay, so at a, the functional value is negative, and at b it's positive, and And the first derivative is always positive between a and b, and the second derivative also positive. So it is convex, like this. So any tangent line within this closed interval resides below the curve of f of x. And it is strictly monotone increasing. This function is because the first derivative is positive. Then there is only one point where this function crosses the horizontal axis. That is alpha. So if we define this sequence in this way, the sequence, let's say, first is, so C1 is this. C1 is equal to B. So, and then C2 is defined as C1 minus f of C1 and f prime of C1. So somehow C2 is defined based on the value of this, and we see what this means exactly. And then somehow this sequence converges to alpha. So somehow C2 is determined by this, and C3 is determined by this, and so on. So this is Newton's method. So in this way, we can solve this equation. So f of x, where f is some nonlinear function satisfying all these conditions. So if you want to solve this, we apply this Newton's method. So, and we approximate the solution step by step until we reach some convergent value. Okay, let's prove this. And as I have already explained, this function takes negative value at a, so there's some negative value, and positive value at b. And it's strictly monotone increasing and convex. So, and also this is continuous because it's twice differentiable. So it is of course differentiable, so it's continuous. Any differentiable functions are continuous. So by the intermediate theorem, which you have learned in a previous chapter, there exists some value alpha that makes this function value equal to 0. So there is some alpha in this interval such that f of alpha is equal to 0. And also, since this function is strictly monotone increasing, such alpha is unique. And that means there is only one such alpha that makes this f of alpha equal to 0. Okay. Now, let us pick any number between a and b. Let's call it c. And draw a tangent line at that point. So tangent line to this curve at this point. Okay. And the equation for the tangent is this. F prime of c, x minus c plus f of c. And now we find the x-intercept. So that is y-coordinate is 0. So we solve this. Let's call it c prime. The x-intercept is c prime. So c prime f of c. And if we solve this, let's do it step by step. So f of c prime, f prime and c prime is negative f of c. If you divide both sides by f prime of c, we have this. And add c to both sides, we have c minus f of c over f prime of c. So if c is equal to cn, then c prime is cn plus 1. Now this is the sequence we have defined in this theorem, if you remember this one. Okay, now this function f of x is convex. So that means this tangent line is always below this curve. Okay, so that means this x-intercept is always greater than alpha. Okay, so this, even if we happen to choose c below alpha, then if we draw the tangent line at that point, the x-intercept will be always greater than alpha. So we may assume that Cn, since we are starting from B, C1 is equal to B. This is the starting point. So we start from B. This sequence value is always above greater than alpha. So this means this sequence is bounded below. So the lower bound is alpha, one of the lower bounds. Okay, and also if Cn is greater than alpha, then this means, from this graph it's evident that the value of f of Cn is positive. Okay, f of, because it's strictly monotone increasing. So if Cn is greater than alpha, then f of Cn is greater than f of alpha, but f of alpha is equal to 0. So this is positive. And by the given condition, f prime of Cn is positive. So this means Cn plus 1 equals to Cn minus f of Cn over f prime of Cn. So this term is positive. So we are subtracting positive number from some number. Therefore, this is less than Cn. Okay. So this means this sequence is not only bounded below, but also strictly monotone decreasing. Okay, so bounded and monotone. So if you remember the monotone convergence theorem, which we have learned before, so by monotone convergence, theorem, Cn converges. Okay, converges to some value in this alpha and b, right? Because we are starting from b, so this is b is C1, and Cn is strictly monotone decreasing and bounded below by alpha. So whatever the value, the limit is, the conversion value is, it is between this interval. So let's say the limit of Cn is beta. Okay, then we have alpha less than or equal to beta, which is less than b. Okay, so let's apply this limit operation to the both hands of this equation. So this will converge to beta, and this will converge to beta, and this numerator converges to f of beta. This denominator converges to f prime of beta, right? So after all, we should have beta is equal to beta minus f of beta and f prime of beta. Okay, so as n goes to infinity, we have this. But this beta will cancel this beta, so the right hand side is equal to 0. So if you just cancel the denominator, we have f of beta equal to 0. However, alpha is the only point where f of alpha is equal to 0. That makes the value of function 0. So therefore, if f of beta is equal to 0, it must be that beta is equal to alpha. So therefore, this sequence converges to alpha, which is the 0 point of the function. Now let's consider a simple example of Newton's method. Just for simplification, let's try to find the square root of 2 by Newton's method. Okay, so square root of 2 is of course the solution of x squared is equal to 2. So we define this function f of x as x squared minus 2. So the square root of 2 is the solution of f of x equal to 0, right? So if you draw the graph of this function, so when x is equal to 0, its value is negative 2. And if you take a sufficiently large value of x, then it is positive. It could be any value as long as f of x is positive. So let's take, for example, 2. So in this case, x squared is 4, so 4 minus 2 is 2. Okay, so that's positive. So we define a sequence. Okay, first of all, we differentiate this function. Then we have 2x. And okay, so that's it. So the sequence is defined in this way. Minus f of x is cn squared minus 2, and this one f prime, maybe I should write more slowly. So f prime of cn, that is cn minus cn squared minus 2 over 2cn. Okay, so this is, let's see, if you simplify this, let's see, cn minus cn over 2 plus 2 over, okay, it's 1 over cn. Yes, so that's, let's see, 1 cn over 2 plus 1 over cn, and that's 1 over 2 cn plus 2 over cn. Okay, so to summarize, we have this equation, this recursive equation. So let's put c1 equals to 2. Then c2 will be 1 half 2 plus 2 over 2. So that is 1/2. So that's 1 times 3. So that's 3. So that will be 1.5. And C3 is 1, 2. And just put 1.5 plus 2 over 1.5. That is, let's see, according to my calculation, that's 1.5, 5 for 2, that should be 1.4166, and so on. So if you continue this, the value will be closer and get closer and closer to square root of 2, which is 1 hitoyo hitoyo ni hitomi goro, something like this. And this can be easily implemented in a computer program. So if you can program, please try to implement this and see how you can find square root of any positive numbers. And that's all for this chapter. See you next time.